Okay, then our next speaker is Darío López Díaz from Pontificia Universidad Católica del Paraíso, Chile. And he's going to talk about BPS black hole with non-abelian soliton in Chern-Simons AdS 5 supergravity. So please, Darío, go ahead. I will let you know when there are 5 minutes remaining.
Okay. First and all, thank you very much for the organization, for letting me give this talk. This is part of my PhD studies, and this is work together with Olivera Miskovic, Laura Andrenopoli, and Gaston Giribert. Well, the context of my talk will be, I will give a small introduction to the subject, then we will study the theory that will be studying this very particular solution of a black hole coupled with a soliton. Okay. Then I will introduce this black hole. We are going to discuss some topological and symmetry charges and some conclusions. So first and all, a very introductory thing to this subject is that say that BPS states are solitonic configurations which are invariant under some supersymmetric isometries. These are very important states due to the fact that they saturate the Bogamongi bound, which is these conditions that appears from the supersymmetry algebra. One example is electrically charged black hole in Einstein-Maxwell gravity. For instance, the mass and the electric charge present this bound, and the existence of these BPS states saturates this bound. I mean, this equality here. That prevents that the black hole solution decay into naked singularities and implements the cosmic censorship. In standard supergravity and string theory, this BPS states is known as a no force condition that makes an equilibrium between gravitational and internal symmetry forces. It's a kind of balance between these two quantities. And it is possible because the introduction of a central extension via topological charges. So these BPS states will depend on the topology of our solution, the symmetry group involved, which is part of the theory, and the conserved charges that we have. Something important to mention is that the Chern-Simons supergravity is quite different from standard supergravity. It is a gauge theory which has an enlarged local symmetries. For instance, it is related with the AdS symmetries. Its AdS vacuum is not, it is degenerate, so we cannot apply perturbation theory as we could do it in standard supergravity. Something else, another important thing is that the black hole entropy is not necessarily proportional to the horizon area. So we cannot give for granted that all the properties of standard supergravity will be applicable to Chern-Simons supergravity. One of the most important equations is this relation between BPS states and the extremality of black holes in the supergravity. So thus this property works in Chern-Simons supergravity as well. We don't know. We are not pretty sure about this. So first of all, we need to construct BPS states in order to respond those questions. So introducing the theory, we first will focus on this solitonic solution in the U1 SU2 sector of the theory. This is a solution without gravity. So first of all, we have to consider, we are considering D=5 Chern-Simons theory on this manifold where this manifold has boundary as a 3-sphere, okay? We call the SU2 gauge field as calligraphic A and the abelian field as A. This abelian field vanishes on shell, and the I corresponds to the 3 angles of the 3-sphere. Something very important is that it has non-vanishing topological charge. So the Pontryagin index is non-trivial, and it's also quantized given via the homotopy group that we are discussing later. So we know that the Pontryagin index is associated with a topological invariant defined of this boundary, the three-sphere. So this Pontryagin index will characterize the winding number of the covering group of our internal symmetry. This covering group will be given by the homotopy group P3 over SU2. As we know, this is belonging to the integers. This is an example of a winding number belonging to the integers, where we can see how the SU2 covers this point in this case, but we can think this point as an S3 sphere. In our solution, the Pontryagin topological invariant will depend on the axial torsion C. This is part of our constants that will appear part of our solution. In particular, this is the axial torsion charge. Okay, so the Pontryagin invariant will have this form, and we can see that it corresponds, for instance, for C squared equal to 1 will be a pure gauge solution, since F depends on this quantity here, and is topologically non-trivial. And for C squared equal to 2, for instance, here will vanish and will be a topologically trivial solution. Now we are going to couple this soliton to a Chern-Simons black hole. So this non-trivial configuration will be given in the framework of AdS5, Chern-Simons supergravity. We know that this is a gauge theory, which is invariant under this supergroup, where the bosonic sector is given by this multiplet. The geometry is contained here in this AdS side. So our black hole will be living here, since all the other rest of our theory will belong to the soliton. The gauge field, which is the thing that has all the dynamics of our theory, is a Lie superalgebra valued of this superalgebra. The components of our theory will be the AdS side, the U1 field, SU4 field, and fermions. Well, this is very well known that in first order formulation, the metric is constructed in terms of field line fields and has this relation with the metric. In our case, the fermions are sources of the torsion field. So this will be an independent quantity. And we are interested in solutions where we have vanishing U1 field. And these are the equations of motion that remains for us. Here, this F are the field strengths of the SU2, SU4, and AdS. So regarding the black hole solution, we're going to consider a metric where it is spherically symmetric and static, where this is the three sphere, which be the boundary of the black hole. The non-vanishing torsion components will be related with the trace component and the axial torsion component. The solution that we found is this set of functions. We have several integration constants, which is the black hole mass, the axial torsion C, which is where it appears in the Pontryagin index, and gravitational hair that modify the AdS asymptotics. Where we have this combination, we will obtain dimensionally continuous black holes. Okay, so the important part here is this constant C square, where will be closely related with the topological properties of the solution. The black hole horizon is defined by this condition, and we can see that appears this is extremality parameter, where give us a kind of separation between two horizons. So when this extremality parameter is vanishing, our black hole becomes extremal. The BPS black hole that we are constructing, we consider that it has a vanishing gravitational hair. So this is the first consideration that we are taking. For the non-abelian field,
Darío.
Okay, thank you. For the non-abelian field, we're gonna break our internal symmetry from SU4 to SU2, since we have studied before that our soliton is living here. And we denote a 3 unbroken generator of the SU2 group as Ti. Well, the solution of the SU2 is the soliton that we previously discussed. So what is a BPS black hole? It's a bosonic solution of supergravity that saturates the BPS bound and also preserves some supersymmetric isometries. And this is the thing that we are going to put more our focus. So we know that our theory is invariant under local on these group transformations. In particular, the supersymmetric transformations of fermions will have this this form. So, since we are considering a purely bosonic solution, this transformation leaves our supergravity invariant. So, via this condition here, we are dealing with a Killing-Spinor equation, which will tell us the supersymmetric isometries at a bosonic level of our supergravity. So if we find a globally well-defined and non-vanishing Killing-Spinor, our bosonic solution will preserve some supersymmetric isometries. Summarizing, the solution without the gravitational hair, and not necessarily in the extremal point, it is characterized by these two quantities here, the gauge field and the field strength, where here we can identify our soliton, SU2 soliton. The non-abelian soliton can be written in this form. In order to solve the Killing-Spinor equation, our BPS solution corresponds to the extremal point. I mean, p squared is equal to 0. It leads us to the globally well-defined Killing-Spinor, given by this quantity here, and these two extra conditions. These two extra conditions are really 3 independent equations, where each one will project half of the original supersymmetry. In that sense, we are dealing with a 1/8 BPS state. Regarding the topological unsymmetry charges, we can see that where we are considering gravity coupled with our soliton, I mean the AdS times SU2, we have to compute a new point-tracking charge. This topological charge is not quantized because the corresponding homotopy group is not set value and is given by this quantity here. We can see that the SU2 topological charge cancel out with the AdS contribution. And the result, the final result, is proportional to our extremality parameter. So the BPS state is topologically trivial in this case. Regarding the gravitational energy, will be related with this constant gauge parameter, and will be given by this equation. And we can see that also it's proportional to p squared. So the energy of our BPS states is vanishing. This is similar to what happened in D = 5 dimensionally continued black holes and BTZ case. Even though our our energy is vanishing, we still have some kind of stability. Regarding the energy spectrum of the theory, if we consider in this convenient mass parameter, we can see here that our extremal black hole is in this point. Then we obtain naked singularity, ADS, and naked singularity again. So if we have a black hole with two horizons, here we have two horizons, and we have started to decrease our energy, the minimum, we can see that the extremal black hole is the lower bound of our energy. In that sense, the BPS bound will ensure that our solution cannot decay into naked singularities, providing stability to the solution. So this is the first example of BPS black hole in Chern-Simons that involves non-abelian fields. Some other examples were global ADS BPS state with non-abelian soliton was found here, and BPS black hole without non-abelian fields here. Without gravity, the non-abelian SU2 field will describe a soliton that will have this quantization. The soliton, is important to mention that alone is not a BPS state. When we include gravity, it will we can form this BPS state, but it will add gravitational energy that unwinds the soliton. So in the extremal case, our Pontryagin index is vanishing. And it is not quantized also. And something that we have to remark is that when we include the gravity, we find this BPS state. This extremal black hole is stable and cannot decay into naked singularities, neither global ADS space. So this is my, thank you.